Good afternoon, everybody. Thanks for coming to the PAC-Trans Regional Transportation Seminar for the autumn quarter. We apologize for the delay. The person who has the key to this room was late, and also we had a technical glitch. Our camera does not seem to be outputting the video to the webinar source. So anyway, let's get this started. It's certainly our great pleasure to have Professor Kelvin Wang to come to PAC-Trans and deliver his recent research on intelligent evaluation of transportation infrastructure, pavements, and bridges. Kelvin and I have been knowing each other for a long time. Kelvin is an outstanding researcher from multiple different perspectives. He was president of the ASCE Transportation and Development Institute, and currently distinguished member with ASCE, which is the highest honor with the American Society of Civil Engineers. Not only Kelvin do research, he also actually developed technologies, and his technologies on survey of pavement cracking and stress has been widely recognized and also followed closely by the industry and the researchers. He has experience from both research and a practical side. Kelvin worked for DOT before he joined academia. So certainly he has a lot of experience about research, technology development, and education. So let's welcome Kelvin to start his webinar.
Thank you, Professor Yinghai, for the nice introduction. I need to point out that Professor Yinghai Wang also was elected to be a distinguished member of ASCE for this year, and the celebration was just last month in Chicago. So ASCE selects about 10 members from the world as its highest honorees, and so I'm happy to be in the same league as Yinghai. I was elected, I think it's 2 years ago. I think that was it, yeah. So it's an honor to be at the University of Washington, and also, of course, the PAC-Trans, which is renowned for its transportation research, and also has been in the UTC Region 8 PI for many years. Before I start my presentation, I need to point out another person who was a mentor for me in the 90s, and he's here. Joe Mahoney, Dr. Joe Mahoney. I got to know him when I became an assistant professor. Actually, when I was an original DOT, I got to know him at TRB, and we actually had more talk, that's 30 years ago, than in recent years. But the words I heard from Joe helped me in my career a lot. So I'm glad he's here, and he just retired last year after about 40 years here, I guess.
Over four decades, yeah.
But he looked the same as I met him 30-some years ago.
You've always had trouble with the truth.
Well, that's a good criticism, but I hope my technical presentation is different from what you just told me, right? Okay, so without further ado, I'm glad we have a bunch of students here. I hope people who joined from YouTube did not get discouraged because of the delay. So I'm going to use maybe I need to exit out, okay.
Maybe just the clip.
Okay.
Sorry.
Thank you, Cole. For those that did not know, I moved to Montana State University 3 months ago to be its director of the Western Transportation Institute. So before I talk about the technical details, I would like to introduce what WTI is. It's a major research institute in transportation in the US, university-based institute. We are best known for rural transportation research. We believe we are the biggest in the world, specializing in rural transportation. It's based in Bozeman, Montana at the university. At its peak, we had $11 million annual expenses with 50 staff members. Right now we're smaller, but we're going to restart the growth again. Our most famous programs are in road ecology. You guys may know what road ecology is. I do have a visual for you. And safety, we do a lot of safety education, outreach, community service. And we have an extraordinary workforce development program. Patron has that as well. And we are proud for our program. Our leader in that program is very well known, and she has been involved at many national panels and forums. So I have made a decision along with the leadership at WTI to grow in safety research, and also the passion I developed in the last few decades, that's automated evaluation. Well, if you tell me what WTI is known for, I would say it's known for this, okay? The interactions between animals and drivers, and how to preserve the well-beings of both spectrums. And WTI is dominating this area on a worldwide basis as a research institute. So we have done tremendous amount of work for federal lands, national parks, different federal agencies, and also different state agencies, and also worldwide. Our researchers are sought after in Asia, in Europe. They go there all the time. For example, our lead researcher will be in Thailand studying elephants. Actually, he probably just left last weekend for Thailand. So this is very interesting. It has very strong societal impact. I just want you guys to know there's a very narrow branch called road ecology, and we are known for that. And you know, we have people specializing in fish wildlife, and he actually worked with a federal agency. Federal government has a lab by Bozeman just to do that. Okay, let's come back to my area of study. In the mid-90s, when I got into the pavement research area, that's when I met Dr. Mahoney. I was doing pavement management, optimization type of work, and I'm sure she reviewed my papers then. But at that time, I was trying to really get to the bottom of data, right? Every research, any types of research rely on data, high quality data. In payments, we never had high quality data. So I had always a passion for computing gadgets as a student. So I went into this area, how to collect the data and how to analyze data, how to provide payment engineers with high quality data. So this is our latest gadget after nearly 30 years of research. We call that Pave 3D 8K. Some of you actually was at my presentation maybe 6 years ago in high. You got me here first time 6 years ago. At that time we didn't have this, so this is very new. It's a 0.5 millimeter resolution full length coverage. You may see that, you know, on the top left there's a vehicle with some Asian characters that actually was in China. We are able to capture payments at 1 millimeter resolution. We also changed and improved it to 0.5 millimeter resolution, complete coverage of the payment lane. And data collection is just one side of the story. The most important part is to analyze the information in 3D at such fine resolution and produce results that payment engineers can use. I'm not going to talk too much about this, just let you know that we did have a paper that was published in 2017. The work started in 2015, and this paper has been cited close to 800 times already. It's not common for civil engineering papers to have such high citation rate. for about 5 years. So it's a fundamental work in this area. I believe like professors like Ying Hai and then his team started working on artificial intelligence and deep learning around the same time. So that was a good time to start the research. I'm going to give you a few slides that are very basic and essentially introductions to what a neural net is. Essentially, a neural net is so somebody, a biologist and computer scientists came up with an idea that, you know, animal brains have neurons. Can we build, you know, neurons in computers? And the answer was yes, you could. And they did that in the 80s with, you know, computers then. It was very basic, and it was able to solve simple problems that you can just do it by hand. I actually played with it 30 years ago. It's kind of interesting. It could solve a quadratic equation, for example, by learning, but that's not very useful to us at that time. So today, it's just we build much bigger neural nets, right? You have multiple layers. The layers can be like dozens or hundreds of layers. And then the connections between among neurons can be hundreds, sometimes thousands per neuron, and that's very, very big. And then example data, we have lots of them. My internet runs like terabytes and terabytes every second. We have this kind of data available to us. And then the processing power is becoming adequate, including the CPU's processing, the memory size, the bandwidth. They all came together just in recent years that are able to handle this kind of problem of a human brain. Deep learning has a unique property, and people who work on it knew this. That's the learning is cumulative. Right? You can structure a network such a level that anytime you add new information to be learned in the same network, the network can become somewhat smarter in some ways. Here's just my understanding. Some of them may be wrong. You tell me. I'm sure some of the PhD students here have done a lot more work than I did. Artificial neurons, essentially simulating human neurons. And then we have a large number of neurons and many layers. And we talk about billions of neurons today. Why we build a neural network is because we need to find a way to determine the weights connecting the neurons. Determining the weights connecting neurons is the critical step in the training. And we use GPU today to do that, and it's very powerful. And we also use very sparse and huge matrix operations. So when people are talking about AI-enabled CPUs, consumer CPUs, that's coming to us this year and the next few years, they essentially build customized matrix operators inside the CPUs that can work with very large and sparse matrices. So again, learning and inferencing are two separate processes. For example, if you use ChatGPT, either use your phones or your computers, that's called inferencing. Application of deep learning in payments is many. We have many applications. For example, any calculation-based classification, like finding cracks and classifying cracks, is just one of the many examples. Non-cracking visual distresses, nearly all distresses on payments are visual, and we'll be able to use deep learning to do that, to do the identification and the classification. I was having a very short conversation with Joe before my presentation. That conversation is going to continue later this afternoon after the presentation. That is how to relate payment surface deflections to layer moduli. Okay, we struggled for nearly 40 years. So I suspect Joe, when he was a PhD student for Dr. Litton, that's like 4 or 5 decades ago, he probably faced the same problem, how to interpret FWD data to relate to layers moduli. And that problem remains after 30, 40 years. And materials properties in general, Okay, we do a lot of lab testing. I assume that in Washington, in Seattle, and maybe Washington State, you have huge materials labs just to do that, and every state has labs to do that. And also challenges in ME-based payment design. We still have a lot of problems in there, and some of the problems maybe can be solved with AI solutions. So I'm going to give you 3 examples regarding how to use AI to solve payment problems or bridge problems. The first one is multi-objective deep learning. Is kind of it can be useful to us, okay? And then safety sensor, how to measure payment safety. I know that your Star Lab here at PacTrans have invested a lot of effort, resources into safety. There's another aspect of safety in transportation, that is the pavement surface safety, okay? It's very, very important, by the way. About 20% fatalities, traffic fatalities in the US are directly related with surface friction. Okay, that's a huge number to us. If you want to really relate to how many people killed, that's 10,000 people killed in the US per year. They died largely because we don't have adequate friction on the pavement surface. Lastly, I'm going to give you some examples on bridge approach evaluations. Finding cracks, essentially, how to do that at high speed, at high accurate rate, without working or not working at times. That's the problem we faced in the last few decades. People can develop very interesting imaging, and the papers will show actual examples that they find all the cracks. But by the time you switch to different pavement in different location, that software fails miserably. Okay, and it happened to us, it happened to everybody else. Now with deep learning-based, cognition-based approach, this method has become very accurate, consistently, okay? And we were the first to do this. Now, cracking is not the only distress we face, right? We have other problems, for example, potholes, cracking seal, and other surface distresses. How to identify those non-cracking distresses as well. And we produced another paper last year in the same journal called Intelligent Pixel Level Detection of Multiple Distresses. That's the result from our work in the last 2 or 3 years. Those, by the way, those colors were not marked by people. They came out of our CrackNet, the deep learning-based network that's able to identify the different problems, including cracking, markings, and seals, potholes, patches. Okay, patches are important. Seal cracking are also important. And we're able to achieve extraordinarily high speed and high accuracy. That's for concrete. So the second topic I'm going to talk about is about safety, right? So at PacTrans, you guys have done tremendous work in safety. It's more on traffic safety, operational safety. That's the cause of most accidents and fatalities. But for 20% of those fatalities that are related to pavement friction, which means when there's water on pavement, how can you control your vehicle without losing the contact? So that's where the safety sensor comes to play. The existing practices of measuring pavement friction are based on contact-based and rubber-based tires. So for those people who still remember high school sciences, right? Newton came up with this kind of idea 300 years ago, actually. I want to make sure, so actually before the presentation I checked Wikipedia. Newton actually is almost exact 300 years. And he defined all those Newton's laws. One of them can be directly applied for friction. So today, 300 years later, when we send people to the moon, when we're able to build a supercomputer for the size of a phone. We're still using a very archaic method of dragging a rubber tire on a pavement surface and put water underneath it to estimate the friction, okay? But the thing is, if this principle works out good, then I'm okay with it. The problem is, the results from this testing are not repeatable, and they're not accurate, okay? And we're still doing it just because we do not have an alternative, okay? But we came up with an alternative. It doesn't mean we're the only party. I think we're ahead of anybody else in the research side. That is how to reconstruct the pavement surface at both micro and macro texture level so that you essentially obtain a digital twin. You analyze this digital twin that is a replica of the pavement surface for friction properties, okay? When we came up with this idea a few years ago, I thought to myself, it's going to be highly repeatable, it's going to be highly accurate, and today's answers are yes. We're able to do better than those contact-based, rubber-based friction testers. Okay, so I'm going to show you some of the data. This was the initial prototype of the sensor to capture the pavement surface data. That was done roughly 4 or 5 years ago before the pandemic. This is actually the sensor mounted in the back of the vehicle. We use the same triangulation principle. You see a laser line, or almost like a chalk mark, a blue. That's actually the laser line under the sun in the summer. Okay, can you see how bright the laser line is? The reason you see the line so thick is because we call it bleeding. It's so bright that it bleeds out the visual, what do you call that? The visual image in your eye. So it's wider than it appears. It's the actual width at its peak power is roughly half to 0.1 millimeter. Now that's the visual data we're able to obtain, both 2D and 3D, roughly less than 10 inches. It's a square. This 2D and the 3D, they are on the same location, as you can see. And see the leaf on the surface? It shows up on the 2D real well. On the 3D, it's very striking. You can see the holes on the leaves, on the leaf. And then we have some examples like we had a core-ring on the surface. One side is 0.5 millimeter resolution. The other side is 0.1 millimeter resolution on the same locations. And then I have some other visual examples. The bottom line is we have been able, before the pandemic, we were able to acquire pavement surface at 0.1 millimeter resolution. Concrete surface, very detailed. So the buzzword here today is, in the infrastructure world, is called digital twin, how to reproduce the infrastructure or the environment or highways or buildings at an extraordinarily high resolution in 3D. We are trying to do very fine resolution at 0.1 millimeter and below, reproduce the pavement surface so that we can analyze for safety information. Those are just some of the visual examples we have for you. And now, for those people who are familiar with the laser triangulation, transversely we're able to get a correct resolution at 0.1 millimeter or 0.05 millimeter resolution in the transverse direction because the sensor's area of interest is fixed. When you go longitudinally at high speed, we get roughly 10,000 lines per second. So for those guys who have a quick mind, can you tell me how many lines per second if you drive 60 miles an hour for 1 millimeter resolution? 1 millimeter resolution, 60 miles an hour. We need to get 28,000 lines per second. So our limitation, sensor limitation is 10,000. So we are off of a factor of 3 to get 1 millimeter. But my goal is to get what? Get 0.1 millimeter. Okay, for those guys in deep learning, you probably, oh, Amazon has been doing super resolution for ages. Same thing as Microsoft, super resolution. We face different challenges, right? Those big companies, the challenge they face is two-dimensional. Right? They work with X and Y. Right? You have very coarse resolution image, but you want to increase the resolution by a factor of 10 in both directions. In our case, we want to increase the resolution longitudinally only. That would give us some advantage, but our challenge is we're not looking at a factor of 10, we are looking at a factor of 100. Can we do that? Okay. Give you some examples of our initial testing. The very small example on the right is the original. Essentially, we downsize the resolution by a factor of 64. And then we use our super resolution technique to reconstruct by a factor of 64. Okay, it's not perfect. It cannot be perfect, but I think it's close enough for us to continue this work. This is the concrete. Ground truth on the right, and then we degrade it by a factor of 64, and then reconstruct through our super resolution deep learning technique. So we got extraordinarily good results. One time I just heard another person talking about pavements regarding statistics. Joe probably can relate to that. In pavements, when we got R square value, if it's 0.6, 0.7, we are thrilled, we are happy. We never had good data, right? Well, I'm not sure about operational people here, and you probably would say this is not really good enough. We're looking for 0.99 or something. Now we're approaching 0.9, 0.8 R square values with results we get from our new safety sensor. By the way, the rubber-based, contact-based friction testers, they cannot get any results close to this level of R square. So some additional results, very encouraging to us. So we're going to continue this for next few years. Okay, so I'm coming to our third topic using our high-resolution 3D sensors for bridge deck survey. This kind of idea came to us from our bridge engineer in Oklahoma, and Walt Peters, that's his name. He is like a university professor. Every time you talk to him, he said, really? Let me take a closer look. Next year, he would give us funding to do it. We had 2 or 3 cycles of funding. Unfortunately, the new project, which is the biggest size project from Oklahoma DOT, we received the project, and then I was leaving. So, but hopefully I still have a role in that project. That's the third project we got from Oklahoma DOT. We all know that bridge decks and bridge approaches are very, very important for safety. Okay, extraordinarily important, more important than pavements itself. So, of course, we use our 3D imaging to identify distresses, okay? And then you can see that we actually surveyed about 60 bridges, interstate bridges for Oklahoma DOT in the last few years. Those are some of the examples. By the way, when we survey the bridges, we don't stop with the highway traffic, right? We just drive our van at 60 or 70 miles an hour, and then we finished. And then we use roughness. Our vehicles are able to do roughness evaluation as well. And then, you know, we can tie roughness data to our 3D visual information, particularly on the approach joints. As you can see, the deteriorations. Those are some of the examples. By the way, Oklahoma bridges do not all look like this. We surveyed 60 bridges. We identified several problems. Those are just examples of the few problems we had. Again, you know, bridge joint roughness in 3D. Hydroplaning on bridge deck is very important. People don't talk about it a lot simply because it's such a high risk, high liability issue. So we don't publish the data. Every time we do that, we have to ask permission. But hydroplaning, you guys know what hydroplaning is, right? Hydroplaning is when your vehicle tires lose direct contact with the pavement surface. So there's a very small, very thin water between, and that will cause the vehicle to lose control. And the Kelvin model is still the dominant method for us to do the hydroplaning analysis. It requires longitudinal grade, it requires cross slope, which we have from our IMU in the vehicle. As you can see, fortunately, for these 60 bridges we have, all hydroplaning speeds based on our analysis, they are all above the speed limit, okay? So that's all good for them. We have 14 values from our 3D. We have roughness values from our 3D system. And also, we have joint distresses. They both visual and also analytical data, they'll come together in this comprehensive solution. As you can see how detailed the 2D and 3D visual data is for bridge joints. Some of you probably took a structural class at your undergraduate level. The impact factor from 18-wheelers is very, very important. Essentially, in layman's term, is when the fully loaded 18-wheelers comes by to the bridge, the big wheels would hit the approach joints big time. Okay, if you ever stood by a bridge and on an interstate and an 18-wheeler comes by, and you hear the boom sound, right? Just because the impact from that, and it's a little bit unfortunate, right? When you go into engineering, especially civil engineering, in every discipline, either pavements or geotech or structures, there are a lot of mundane issues. You think that it's so simple. As I told you guys earlier, we sent people to the moon 50, 60 years ago. We have a supercomputer in your pocket. Today, we do not have a universally accepted technology to determine impact factors of fully loaded 18-wheelers on bridge approaches. I just figured this out a couple years ago when we started doing the project for ODA. I asked Walt, I said, do we have standards? He said, well, there are some recommendations in ASTRO guide, but no supplier has a solution how to find out. So you know what we're doing today? We're using our 3D vehicle with our longitudinal profiler to essentially find out the IRI first, and then they study the impact. This is the cheapest method today for us to do the so-called IM estimation. If you search this is a hot topic everywhere, in the US, in China, a lot of literature, but there's no solution. I do not know if I exceeded my time. I just really talked about some examples of my recent work. A lot of people think that AI or deep learning is just a buzzword for people to get funding, but it's really not true. Okay, we really can use AI to solve real problems. We've done that, and in-house team, the Star Lab at Pavement have demonstrated that you guys can solve a lot of problems in the traffic operations, and the future looks very, very good. Can you imagine that you can put a $100,000 GPU into your cell phone in 5 or 10 years in that time frame? Then the phone can do wonders for people, helping people, translating, helping disabled, elderly, and all those things are coming along very fast. So, in the future, we have been working on self-learning. I'm sure you guys have done that as well. It actually works. I'll just give you an example. I haven't shown that yet. We can use GAN's technique, right, GAN, to generate cracking information automatically. Generating a high quality cracking image takes about 5 to 10 minutes per person. It takes another person the same amount of time to verify it. And then by the time you have one visual that can be used for training, it's easily 10, 20 minutes of labor. Okay, we've done that. We generated 10,000 pairs in 2015 to 2016. And we're done. We cannot go back again. It's too expensive. We hired 6 people, 3 pairs working for a full year, full time. How to use AI technique to regenerate your training data, right? Like on the fly. Fortunately, we don't have to work on the fundamentals because Google, Amazon, Microsoft, each of them have like several thousand people working on this problem every day. So multiple detection, multiple objective is an interesting problem for us. And we want to really use AI techniques to solve pavement design problems as well, including how to relate surface deflections to pavement layer strength. Of course, our big effort in the future years will be a line contact 3D safety sensor. We just funded by Federal Highway Year program. I can tell you guys the contract was just signed recently, so you guys probably heard of it. It's a reasonable amount of money, but everything helps. UTC money, Federal Highway money. So I hope that funding would help us to not really develop the technology per se, really show results to Federal Highway people that this thing actually works better than your rubber and contact-based friction testers. Okay, that concludes my presentation. I'm not sure, Yinghai, you would allow me to answer questions or? Thank you.
I have 2 questions.
Yes.
Earlier on when you were talking about the evolution of your sensor, you mentioned on a few of the slides it said processing speed and it was measured in kilometers per hour. Is that how fast you can drive and still process the data accurately?
Our processing speed today, those are old data, by the way. The processing speed we can achieve today is several times the speed of driving.
Okay.
So
that's good.
It's very fast. Just give you a perspective. For those guys who've done deep learning, the third year, the fourth year PhD students would know, we started with 1080 Ti GPU. You guys still remember those old GPUs? We still use them? Okay. Now we switched to 3090 Ti GPUs, which is about 3 years old. Okay, and we have not switched to 4090 yet. 4090 probably is, I don't want to pay this kind of money for a GPU, but 3090 Ti GPU can get us to 200 miles per hour.
Okay. And then do you have to be driving at a consistent speed?
No, any speed.
Okay.
I have a question.
Yes.
Hello, Kevin. I think it's a fantastic presentation. Thanks a lot for sharing this kind of excellent product for us. So I have a question about, because you used the GAN to try to generate more details from the original data you collected, right? So I would like to ask what kind of loss functions or how to validate this kind of, if it's accurate or not.
Yeah. Joe may know this guy's name. He's from South Dakota. He invented the South Dakota profiler.
Oh, yeah. It escapes me. Put me on the spot now. I can't.
His name just escaped me. He has been selected. If you heard of the South Dakota profiler, it's this guy 40-some years ago, when he was a fresh engineer, he invented a method to measure pavement profile. That's been used worldwide today, and everything's free, and he didn't make a penny out of it other than paid by the state government. So a few years ago, I showed this GAN technique to him in a federal highway project panel, and he was the chair of it. So he looked at me. He was very suspicious. He said, "How can you make up data and then use the data to train things?" That's a valid question. Some of the data we generated, if I don't tell you that it's a fake, it's a pavement with cracking, you probably say this is really cracked pavement, you know, it's not a good pavement. And then if I tell you it's fake, you say, look at the details, it's not, yeah, there's some differences, right? The answer to you is using GANs to do that, it's not perfect. If we tell you, if I give you 10 of them real cracked pavement, the other 10 images are kind of fake, you probably can tell.
Okay.
Yeah. So we're not at the level that we can really produce a fully cracked pavement that look like real. That you know something's wrong somewhere. Okay.
Okay. Okay. Yeah. The reason why I ask this question because we also use GAN to try to remove the noise from our image. You know, our lab did a lot of job about computer vision. So when you use the camera to capture this kind of images, you may see there's a lot of noise, like the raining, the dust on the camera. So you want to just remove that. This kind of opposite direction of your research. You want to get more details of these cracks, but for us, we want to just remove. So I think maybe we have, even though we have the different direction, but we have the similar approach, right? We use the similar approach to realize a similar kind of product. You want to get more details, and I want to remove this kind of cracks. Yeah. So it's quite similar. So I want to ask this question to ask for your experience.
I think you guys are in better position because the problems you're dealing with are very similar to those problems that are being dealt with by Microsoft, Amazon, and Google people.
Okay. Thank you.
Right. Sometimes they publish papers. Those papers are very valuable. They don't tell you everything. They put the network, you know, in some platform you can try and test. But I don't know how that's going to last, right? And each of them have several thousand people just working on this kind of problems every day. If they put everything in the platform that's for free, you know, that's great. But what happens in 5-10 years, they shut it down and people have to pay for it, you know, so, yeah.
Thank
Very
you so
good.
much. Thank you so much.
Any online questions?
So, Kevin, I have a question. So, you showed us several models with very high correlation coefficient. So, in your opinion, that's a big improvement from the classical methods, right? So,
Yeah.
what make that difference?
I think the classification side, the cognition side of the deep learning, they are way better than traditional statistical methods. That's my answer there. So I think deep learning has a lot to go, but it's going to change. So, you know, for me, I'm glad to lead a team that with people who are really smarter than I am, to be honest. Otherwise, I cannot make this kind of progresses. But I think in the next 5-10 years, it's going to have such a giant leap everywhere that a lot of people will be scared. So the young people here, I think, yeah, I don't know what the future is, to be honest. But what happens, they can do things, you know, for you, much better. Yeah, those cognition capabilities are real in deep learning. Finding cracks is just a very narrow, small example. It's kind of scary in many ways, simply because people say ChatGPT 4 doesn't have a soul, doesn't have intelligence, everything's correct. It's just a huge search engine with some cognition built in. They're all correct. But what happens to, you know, version 5, version 8, version 10? So Joe, you really retired too early.
Oh, not really. Kelvin, I got a question. I mean, okay, so you've made some huge progress in sort of scanning and data analysis, and you're probably right on the cutting edge of anybody in this business. I suspect you're it at this time. Is it beginning, or have you beginning, when you were in Oklahoma, I mean, you just got to Montana, but when you were in Oklahoma, were you moving some of this into their decision-making process on what they were actually going to do to those roads? Was that shifting over, or is that yet to come?
We are not doing that ourselves. One thing I didn't tell everybody, but maybe there's a commercial operation of this technology. So we have users in, for example, in China, in Japan, South Africa, India, Federal Highway Administration, Federal Aviation Administration, FAA, U.S. Army Corps, they all have our systems. They are doing that.
So they're making the transition on the decision making.
Right, so when those people, they pay for the technology, the equipment, and the software. There's a company out there in Maryland, they bought our system. And they are profitable. Sometimes they complain to me just because they wanted more service, but yeah, so they are solving problems for state and local agencies.
Okay.
So it is there. The biggest challenge, Joe, I have had with this is I don't have marketing. Right? I'll give you an example. When the manager from Army Corps of Engineers in Mississippi, you know some people there
Oh, yeah.
in Pavements. There's a senior manager, I knew him. He's a newcomer. He's not the first generation people you knew. He's a newcomer, younger than I am. I don't remember his, I never remember his name. I saw him one time Dynatest reception. Hey, who you work for? During the pandemic, he sent me an email. He said, the FAA folks use your system. They had a good word for your system. I'd like to have one. I said, really? What's your name? So we started talking on the phone, and he got my system. The moral story of this kind of incident is I don't have marketing. Some of those guys actually came through seminars like this. One guy from Brazil, 8 years ago, he wrote me 2 emails. You know all the spams that come from South Africa and Brazil, and I said, this guy's spamming me. He said, the third email said, I already got my visa, I bought my ticket, I'm gonna see you, like, next month. I said, okay, this is real. So I received this guy's name in July, and he got 2 systems. That's like almost 10 years ago. So marketing is hard, and so we don't have marketing. It's a big problem, Joe. Maybe, hey, maybe retirement job?
No, I understand what you're saying. That's one of the problems with public infrastructure in general.
Yes,
Is
very hard.
that we don't jump on appropriate technology as quickly as we might, as people expect us to do, but that you just identified the problem.
Yeah. Also, this, by the way, the
I
guy.
sometimes think we should take an advertising course, quite frankly.
Yeah. This area is so narrow. It's way narrower than you guys working on. Traffic safety, operational is much bigger market. This area is very narrow. Yeah, spend lots of money hiring a full-time marketing guy is a huge challenge. Just the risk.
All right, so given the time constraints, so we'll just conclude here. Thank you very much, Kelvin.
Thank
for
you.
your time. So we apologize for, the webinar people cannot really see the live images. So there are some kind of connection problem there, but we'll post the recorded video online so people can still see Professor Kelvin Wang's talk. And certainly, Professor Wang demonstrated the power of deep learning and AI. And as the chair of the TRB AI committee, we're putting up a conference, hopefully to launch in 2025. That's going to be AI in Mobilities conference. So if you're interested in this, maybe pay attention to this particular conference. So thanks again, everybody, for coming to this seminar and webinar. Thanks, Kelvin, for delivering this wonderful research. So we have the pizza and drink here, so feel free to help yourself. We have about, this room is